Albert Lilly, I'm going to talk about public key encryption. Here is an outline, okay? What is it? Why would you want to use it? What is of interest or what is notable? 4 variables go into forming 2 keys. We have syntax and constraints. We have a spreadsheet model, we have a JavaScript model, and we have ideas for teaching. Okay, basically, the bank wants to get information from you that you wouldn't want anybody else to have, your credit card number, and so several customers need to be able to send their credit card number to the bank, and the bank can send back a digital signature, and only the bank can do this. 4 notable things. One has to do with the fact that in a virtual world, only 1 key is needed. A support for why am I doing this is safer in normal circumstances to transport your number over the internet than to give a waiter your card. And we'll talk a little bit about that. And the ball is in the code breaker's court. The same set of keys is used for all customers. You know, the bank only needs to give out the public key. This is not true of a safety deposit box. A safety deposit box, each customer needs their own key to get into their box. But in the virtual world, it's really nice because 1 key serves all customers. Why do we study theoretical math? The greatest mathematicians in the world did not think that this type of math would ever be useful. What can you do with prime numbers? What can you do with remainders? Yet, if we hadn't had people studying theoretical math, we would not have been ready when the time came. So it's important for people to study theoretical math. Under normal circumstances, when your numbers from your credit card are transmitted over the internet, they're encrypted. They're not readable. So it's actually safer to send this information that's not readable than a credit card, because the waiter can read the credit card numbers. The numbers that you send over the internet are not readable. And finally, this is like a game. You have the code makers, and somebody breaks the code, and then the code maker makes a better code, and the code breaker breaks that, and it goes back and forth and back and forth. Since 1977, the code makers have been in charge. The code breakers have not been able to crack public key encryption. These are the variable names, E, P, Q, and D. These names were given to us by mathematicians. Software engineering would not allow such short names. We would use meaningful names, but the mathematicians don't understand that, and so they use these 4 short names. P times Q is key because, not in our example that I'm going to show you, but in the real world, these are huge prime numbers. And when you multiply these 2 huge prime numbers, you get a number that's not easily factored, and that's why it's so secure. It would take centuries to find the number, to find the factors. Here is an expression. Students need to be able to evaluate expressions. It turns out that in this case, E must be less than the quantity minus 1 times the quantity Q minus 1. We'll see this theme will be shown over and over, that E must be this or E must be that. If it's not, if the constraints don't hold, pick a different E. Okay, we need to find the remainder. This is done with a prefix operator in a spreadsheet. Okay, so a prefix operator precedes the two operands, and 3 goes into 26 8 times, remainder 2, the answer is 2. Here, 30 goes into 26 0 times, the remainder is 26. This is an infix operator. This is JavaScript. So with the infix operator, the operands surround the operator. So you get the same result with different syntax. Here is a constraint that must not equal 0. If it does equal 0, pick another number for E. Here's a constraint that must equal 1. If it does not equal 1, pick another number for E. Here we're going to use this example, these numbers. D is calculated to be 8,743. D must be a integer. We're doing real division, and D must not have a fraction, otherwise pick another number for E. Now, here's the formula that does the encryption. We're going to send the message yo. Y is the 25th letter in the alphabet. O is the 15th letter in the alphabet. So here we have Y to the E power, and it turns out that 2,704 to the 8,743 power is too big a number for the computer to handle. We can interleave. We can do a multiplication, get the remainder, do a multiplication, get the remainder, back and forth, back and forth. That keeps the numbers from getting too big. All right, here is the model, the results of the model. We're taking Y and O. Y is converted from 25 to 2,704. O is converted from 15 to 503, and then we convert them back. This whole model can be done. Here are the formulas. If you understand how to fill down in a spreadsheet, and you understand how to define names, you can do this whole model, decrypt the message. Notice that E is 7, okay? E is 7, 3 didn't work, 5 didn't work, but 7 works. And we fill down to row 7, okay? D is 8,743, and if I go back one slide, you can see we fill down to row 8,743. So that is the spreadsheet model. We also have a JavaScript model. Here are the results of the JavaScript model, the same results. Here are the initializations. We're initializing our variables. Now, here is the encode loop, here is the decode loop. The encode loop executes 7 times because E is 7. The decode loop executes 8,743 times because that is the value for D. The variable myString is something I use to print things out. Now, here are some teachable things we can do to teach. Evaluation of expressions, very important. Assignment statements, loops, we can do iteration. And then we can assign students to write a program to check to see, to compute D, and then check to see if we need to pick another E, that D is unacceptable in some way. And finally, here are my credits.